Welcome learners in the series of videos on topology. This is video number 64 and we are talking about the compact spaces. In video number 63, that is the previous video, we have discussed about the totally bounded matrix spaces. Okay, let us recall a matrix space X is called totally bounded if for epsilon greater than 0 there exist finitely many epsilon balls which will cover X. And we have taken two examples where we have proved every compact matrix space is totally bounded and every totally bounded matrix space is bounded. Okay. Let's see some results, some theorems out of this where we will use the previous knowledge as well. So first theorem, we can say that if X is sequentially compact matrix space, sequentially compact metric space, then X is totally bounded. So if we have a sequentially compact matrix space, then we need to show that X is totally bounded. Let us prove this. Proof. Let us recall that a sequentially compact matrix space is a matrix space wherein every sequence has a convergent subsequence. So let us assume that X is sequentially compact. So let X be sequentially compact matrix space. We need to show that X is totally bounded. Okay. For the contradiction, let us suppose that X is not totally bounded. Okay. Suppose X is not totally bounded. Is another way to prove any statement. Right? Let us assume that X is not totally bounded. Let's see what contradiction we will get. Okay. So if X is not totally bounded means what? For the definition of totally bounded, let's go back. The definition says for all epsilon greater than 0, there exist finitely many epsilon balls. Okay, and not bounded, not totally bounded means there will be some epsilon greater than 0 such that it will not have a finite epsilon balls. Okay, so since we said that X is not totally bounded, this implies there exists some epsilon greater than 0 such that no finite number of epsilon balls covers X. Right? So let us use some induction and derive a sequence. Finally, we need to find we need to use the hypothesis that is sequentially compact matrix space. Okay. So by induction, let us choose. We choose say x1, x2, xn belongs to a set X such that this xn will not belong to union say k from 1 to n minus 1 all around xk of radius epsilon, this given epsilon. Okay, why this is possible? Why this we can do this? Because so let us take x1. Okay, let me write here. Let me write here first. So epsilon covers X. Okay, so let me write here. Let x1 belongs to X. Let us take one point X next. This implies ball around x1 of radius epsilon will not be equals to x. That means there is a point in x which is not in this ball. Okay, let me put that using good statements. Then I will write the next statement, otherwise it will be a difficult task. So let x1 belongs to x such that this implies ball around x1 of radius epsilon will not be equals to x. This implies there exists some x2 belonging to x such that x2 will not belong to ball around x1 of radius epsilon. Okay, now let us take ball around x2 of radius epsilon. Okay, so now let us take since ball around x1 of radius epsilon union ball around x2 of radius epsilon is not equals to x because x is not covered by finite number of points. This implies there exists some x3 belonging to x such that this x3 will not belong to union I from 1 to 2 ball around xi of radius epsilon. Okay, so hence by induction, say by using this argument by induction, we choose say x1 x2 like this xn belonging to x such that this xn is not in the union of the previous balls I from 1 to n minus 1 ball around xi of radius epsilon, and this is possible because x is not equals to union of this, right? This is possible. Let me write for you. This is possible as x is not equals to union I from 1 to n minus 1 ball around xi of radius epsilon. Okay, by hypothesis. So we can do this. So we got a sequence xn here. So since we have assumed here that x is not totally bounded, what we expect is this xn will not have a convergent subsequence, and that will be the contradiction to our fact that x is sequentially compact. Okay, so let us claim that this xn, the sequence xn, the way we have generated this n belongs to natural number, does not have a convergent subsequence. And this will be the contradiction to the fact that x is sequentially compact. Okay, so to prove this claim, let us take m and n. Let m and n belongs to natural number, and let us say that m is less than n. Okay, then this xn. Now remember this n and the previous n is different. Okay, you can use p here. Okay, let me use p. Let p and q I will use. Otherwise, you will say that this m and p is same. Let p comma q belongs to n such that p is less than q. Okay, this implies this xq will not belong to union previous terms. So I from 1 to q minus 1 ball around xi of radius epsilon. If xq is not in this union, of course this xq will not be in the union of up to p. So this implies this xq also will not belong to ball around xp of radius epsilon. This implies what? The distance between xq and xp is greater than or equals to epsilon here. This will belong to this ball if and only if distance between xp and xq is less than epsilon, and this is not here, means this implies distance between xp and xq is greater than or equals to epsilon. What does that mean? This will not have any, this will not be a Cauchy. Okay, so this implies hence no subsequence of this sequence xn, no subsequence of xn is Cauchy, right? And if it is not Cauchy, of course, and hence if it is not Cauchy, it cannot be convergent. None of them converges, right? Now we are saying this because we know that every convergent sequence is Cauchy, but every Cauchy sequence need not be convergent. Remember that, right? So here we have convergent implies Cauchy, but remember the fact that Cauchy need not imply convergent, right? And if Cauchy implies convergent, if every Cauchy sequence is convergent, then we say that the space is complete. Okay, remember this fact. Now we use this first one. So it says every convergent sequence is Cauchy. So of course, if it is not Cauchy, it cannot be convergent. Now here we are using the same fact. That a subsequence cannot be a Cauchy sequence, and if it is not Cauchy, it cannot be convergent. And this is contradiction. This is contradiction to the hypothesis. What is the hypothesis? That we have a sequentially compact matrix space, right? And hence X is totally bounded, right? So we have proved that every sequentially compact matrix space is totally bounded. Also we can show that if X is sequentially compact, then X is compact. Okay, let's do it in brief. It's very simple. Theorem. Let us prove that let X be a sequentially compact matrix space, then X is compact. Okay, remember the last statement. The last statement is if it is sequentially compact matrix space, then it is totally bounded. Okay, and now we are proving that if it is sequentially compact, then it is compact. Okay, so let's do this proof. Very simple proof. So we need to show that X is compact. So let us take an open cover for it. So let us take open cover. U alpha belongs to I, B, and open cover for X. Open cover for. Okay. Now, since we have this open cover, we know that there is a Lebesgue number. So let us take that Lebesgue number. So let delta greater than 0 be a Lebesgue number. So we have already proved this fact. Open cover has a Lebesgue number. Then let us take that delta to be its Lebesgue number, and the fact that every sequentially compact matrix space is totally bounded. The last theorem. Okay. So since X is totally bounded, we have, according to this delta, let us take this delta by 4. Let us take the epsilon to be delta by 4. Okay, so there exist, say, finite numbers, say x1, x2, up to xn belonging to x. Let me write here for your information. For epsilon equals to delta by 4. Of course, delta greater than 0 means delta by 4 will be greater than 0. So we have finite number of points in the space X such that this X will be contained inside union, say K, from 1 to n, wall around xk of radius delta by 4. Delta by, okay, if we change this delta by 4 to say delta by 8, these points will be different, maybe different. We cannot say will be, but maybe different, maybe same. Okay, so this x will be contained inside ball around union of ball around xk of radius delta by 4. Now since the diameter of ball around say xk of radius delta by 4 is less than or equals to delta by 2, we have open ball, and then the of this of radius delta by 4. And of course, the diameter of that point will be less than or equals to delta by 2, and of course that is less than delta. So we have, which is this open ball, the diameter of this is less than delta, and hence by using the previous theorem which we have proved for the Lebesgue number, okay, that is video number 61, Lebesgue covering lemma, implies this is open cover, so this implies there exists, say, some number alpha k belonging to I, indexing set I, such that ball round xk of radius delta by 4 will be contained inside u alpha k. Okay, when this happens for each k, let me write here by Lebesgue covering lemma. Okay, Lebesgue covering lemma. So for each k, this happens. Okay, and therefore what we have is x will be contained inside union k from 1 to n, wall round by using this wall around xk of radius delta by 4, and wall around xk of radius delta by 4 is contained inside u alpha k. So this contained inside union k from 1 to n u alpha k, and this is our finite subcover. So we had the open cover here, we had open cover u alpha belongs to I, and we got the finite subcovers which covers x, and this implies x is compact. Okay, let us take another result. Let me not prove it, I will leave it as an exercise, you can try it. Let us take that as also a theorem. We can show that let x be a complete totally bounded metric space. So we have complete totally bounded metric space, then we can show that x is sequentially compact. And if it is sequentially compact, just now we have proved that every sequentially compact metric space is compact, and hence this will be, x is compact by using last theorem. So we can show that x is complete totally bounded metric space, then x is compact. Right? In this case, we are showing that x is sequentially compact. By using the last theorem, you can say that x is compact. Okay. So till now, whatever we have done, let us summarize it. Proof of this, I will leave this as exercise. Proof this size. So using all these results till now whatever we have proved, let me just write the theorem. Proof we already given. You can write the proof by one assuming the statements. For a matrix space X, matrix space X, the following are equivalent. So 1 implies 2, 2 implies 3, something like that. Equivalent. So first one, X is compact. Okay, if X is compact, we can prove that X is limit point. In fact, the proof of this is already done. You just have to write it. So X is limit point compact. It's a matrix space. We prove that X is limit point compact, then X is sequentially compact. X is sequentially compact. We proved that X is sequentially compact, then it is compact. Also, we proved that if X is complete and totally bounded, then it is compact. So X is complete and totally bounded. So we can do this. Okay. In fact, we have put all those equivalent statements in the previous classes, previous videos. Okay. So I hope you will do it. Now in the next video, we will talk about locally compact spaces. Okay. So see you in the next video.